Welcome back. In Section 8.6, Hypothesis Test Errors and Statistical Power, when testing a hypothesis, we are testing a claim and deciding whether to accept or reject the claim. The actual situation of the claim may be extremely challenging to impossible to know. That's why a hypothesis test is needed. Because it includes uncertainty, there is a chance of containing an error in its conclusion. Therefore, there are 4 possible scenarios for a hypothesis test that are summarized in the table shown in the slide.
Let's define Type 1 and Type 2 errors. Type 1 error happens when, in reality, the null hypothesis is true, but it is rejected during the conclusion of the hypothesis testing. Type 2 error happens when, in reality, the null hypothesis is false. However, it is not rejected by the hypothesis testing procedure. An alternative way to express the Type 1 and Type 2 errors stands in the following table, since H0 and HA are complementary to each other.
As an illustration, let's use the justice system analogy, where a person is presumed innocent, H0, until proven guilty, HA. Type 1 error happens when the court decides to convict someone who is innocent in reality, while a Type 2 error happens when the court decides to acquit someone who is guilty in reality. How to decrease Type 1 errors in a hypothesis test. Since we cannot be 100% confident, we may choose a confidence level, CL, or a significance level, alpha, equals 1 minus CL, that decreases the probability of committing a Type 1 error. The probability of a Type 1 error for a hypothesis test is at most alpha%. This implies that the smaller the confidence level, the lesser the chance of committing a Type 1 error. Type 1 error falls under the responsibility of the researcher who chooses the value of alpha. An alpha equals 5% is a typical value used in most hypothesis testing studies. Type 1 error is illustrated in Figure 8.5. Suppose that the null hypothesis is true. In real life, we don't know. That's why we need statistics. If the sample is bad enough to produce a sample mean that is very different from the true population mean, and thus falls in the rejection region, then we would reject a true mean, hence committing a Type 1 error. Pause the video and have a look at the relationship between Type 1 error and alpha. What about Type 2 error in a hypothesis test? Let's consider that the true mean is not the hypothesized population mean, mu0, but rather a larger alternative population mean of mu-a, as illustrated in Figure 8.6. The distribution will then be shifted to the right because its center is mu-a, referred to as the new distribution. Notice that the old distribution, with a mean of mu0 equals 3, and the new distribution, with mu-a equals 4, share the same critical mean which defines the two regions, support H0 or do not support H0, in both the old and new distributions. Beta is simply the area under support H0 in the new distribution. This slide shows Figure 8.6 of Type 2 error. We are testing the wrongly claimed hypothesized population mean in the new distribution, whose center is the true population mean, or the alternative population mean. Since these two curves share the same critical mean, but not the critical z, it is enough to find the z value in the new distribution to find the value of the Type 2 error, referred to as beta. Let's define the power of the test. The probability of detecting a false null hypothesis is equal to 1 minus beta. To detect, and therefore reject, a false null hypothesis is the researcher's goal. Therefore, 1 minus beta is called the power of the test. The power of the test may be increased by increasing the sample size and decreasing the uncertainty, which is the variance. Enough definitions.
Let's have a look at the cheat sheet to find the value of the type 2 error and the statistical power for the right-tailed test. Step 1. Calculate the critical mean that corresponds to the critical z-value with the formula shown. Step 2. Draw the new distribution with the newly claimed population mean. Step 3. Find the new z-value of critical mean that is situated in the new distribution called z-beta and use the formula as shown. Step 4. Find beta from the z-table. Statistical power is therefore equal to 1 minus beta.
Let's work an example on type 2 error and statistical power for a right-tailed test. A survey conducted on a sample of 25 observations produced a sample mean of 3.5 with a standard deviation of sigma equals 1.5. A. Conduct a hypothesis test that claims that the population mean is at most 3. Use alpha equals 0.01. What is the probability of committing a type 1 error? What is the value of the critical mean? B. We were later informed that a miscommunication had occurred and that the true population mean is 4. Calculate the probability of type 2 error committed in question A. What is the value of the statistical power? Let's work through the cheat sheet provided in the textbook to work this problem. Step 1. Claim that population mean is at most mu less than or equal to 3. Step 2. Define the null hypothesis H sub 0 states that mu less than or equal to 3, and the alternative hypothesis H sub A states that mu is greater than 3. Step 3. Extract the needed statistics from the data. Step 4. Calculate the test statistic using the shown formula. Step 5. Find the critical value by using the z-table or Microsoft's Excel. Finally, Step 6. Conclude. There is not enough evidence to reject the claim that the population mean is at most 3. The probability of committing a type 1 error in this statistical analysis is alpha equals 0.01. Calculate the critical mean with the shown formula to find x bar equals 3.699. Consequently, any value of the sample mean larger than 3.699 will fall in the rejection region of H0. For example, let's say that our sample mean is 3.72, and the test statistic, z, equals 2.4, which is larger than the z-critical of 2.33. Therefore, H0 is not supported in this case. Question B. Oops, the true population mean is at most 4. Let's find the probability of type 2 error committed in question A. Step 1. Calculate the critical mean, x bar critical, that corresponds to the critical z-value to find 3.699. Step 2. Draw the new distribution with the alternative population mean of 4, as shown in the figure. Step 3. Find the new z-value of x bar critical that is situated in the new distribution using the shown formula, and find negative 1.0033. Step 4. Find beta from the z-table. Negative 1.0033 corresponds to a probability of 0.1578, which is the type 2 error. Alternatively, use Excel as shown. Therefore, beta equals 0.1578, and the statistical power is 1 minus beta equals 0.8422. How to decrease the type 2 error. Recall that the type 1 error can be determined by the significance level only alpha, regardless of the sample size n, the standard deviation sigma, or any other parameter. On the other hand, the type 2 error, measured by beta, depends on these parameters.
Observe how the probability of a type 2 error changes as the alternative mean, mu of A, moves closer or away from the hypothesized population mean, mu naught. The surface designated beta changes, therefore the test power, 1 minus beta, changes as well. Continuing our discussion about the type 2 error, this figure shows that if the values of the hypothesized population mean and the population alternative mean are close to each other, mu 0 approximately equal to mu A, then the probability of type 2 error will be at its maximum, with a value of 1 minus alpha. This implies that the actual mean is far different from the hypothesized mean. The next figure shows that as the alternative population mean, mu A increases as the probability of type 2 error decreases, represented by the surface beta. When mu A aligns with the critical mean x bar critical, then the probability of type 2 error and the power are both 0.5. Additionally, as the alternative population mean, mu A, moves further away from the hypothesized population mean, mu 0, the probability beta approaches 0 and the power approaches 1. This is illustrated in the following figure. There is a unique type 2 error probability beta for each value of mu A. When mu naught is close to mu A, beta approaches 1 minus alpha and the power approaches alpha. When mu A aligns with the critical mean, x bar critical, beta and the power are both 0.5. When mu A gets much more bigger than mu naught, beta approaches 0 and the power approaches 1. How can a researcher set up the value of beta, type 2 error, and the power of the test? We have seen so far that if we decrease the probability area beta, we effectively decrease the type 2 error, and we increase the power of the test. But what a researcher can effectively do to set up a value of beta? A sample size of n can be chosen to satisfy the value of the critical sample mean in the two distributions, with centers mu 0 and mu A. This is accomplished by manipulating the relation for the x bar critical to find the appropriate value of the sample size n, as shown in the slide. Pause the video and have a good look at the cheat sheet to set up the type 2 error and the power of the test to find the required sample size n with easy 4 steps. Let's solve the following problem. Consider the following null and alternative hypotheses. H sub 0 equals mu 0 equals 1.5. H sub A equals mu 0 not equal to 1.5. With alpha equals 0.1, standard deviation sigma equals 0.5, and sample size n equals 50. Question A. If the true population mean is 1.55, determine the value of beta. Question B. Calculate the power of the test. Question C. Find the appropriate value of the sample size for a beta equals 0.2 when the true population mean is 1.55. What is the new value of the power of the test? Verify your results and draw some conclusions about the new sample size. Pause the video for a few minutes and try it. Let's use the cheat sheet provided in the textbook to solve this problem. Having the alternative hypothesis, HA, stating that mu sub 0 does not equal 1.5, implies that this is a two-tailed test. Having alpha equals 0.1 implies that z sub alpha over 2, or z sub 0.05, is equal to 1.64. Question A. Step 1. Critical mean with the given formula to find 1.6159. Step 2. Draw the new distribution with the newly claimed population mean as shown in the figure. Step 3. Find z sub beta for mu sub a equals 1.55 by using the given formula to find 0.9319. Step 4. Find beta from the z-table or using Excel to find beta equals 0.8243. Question B. Calculate the power of the test equals 1 minus beta equals 0.1757 as shown in the figure. Let's do question C. Step 1. Mu sub a equals 1.55. Step 2. Beta equals 0.2. Step 3. Z sub beta equals 0.84. Step 4. Solve for the sample size to find n equals 615.04. Use n equals 616. Make it a habit to verify your calculation by using alternative methods. X bar subcritical equals 1.533 gives beta equals 0.2 by using the shown equations. The sample size has increased significantly because beta has decreased significantly from 0.8243 to 0.2. The researcher must consider the costs incurred to sample such a large population. Let's solve another problem of a type 2 error and power of the test, this time with a left-tailed test. Find the probability of a type 2 error when the true population mean is 49,000 and the following information is given in the slide. Pause the video and try it. Follow the steps given in the cheat sheet as follows. Step 1. Find the test type. HA, mu less than 200, then it is a left-tailed test with mu 0 equals 50,000. Alpha equals 0.01, then Z alpha equals 2.33. Step 2. Find the critical mean. X bar critical equals 49,258.6. Step 3. Draw the new distribution with the newly claimed population mean as shown. Finally, steps 4 and 5. Step 4. Find Z sub b for mu sub a equals 49,000. Use the shown formula to find Z sub b equals 0.8127. Step 5. Find beta from the z-table or using Excel. Z sub b equals 0.8127 implies that beta equals 0.2082 and power of the test 1 minus beta equals 0.7918. Let's do another example of a type 2 error and power of the test with a right-tailed test. Find the probability of a type 2 error when the true population mean is 250 and the following information is given in the slide. Pause the video and use the cheat sheet provided in the textbook to solve this example. Once you saw a few examples, the procedure becomes quite easy. Step 1. Test type. This is a right-tailed test with mu sub 0 equals 200. Alpha equals 0.05, therefore Z sub alpha is 1.64. Step 2. Calculate the critical mean to find critical mean. X bar critical equals 233.8756. Step 3. Draw the new distribution with the newly claimed population mean. Finally, steps 4 and 5. Step 4. Find Z of beta using the given equation. Z of beta equals negative 0.7806. Step 5. Find beta from the Z-table. For Z of beta equals negative 0.7806, we have beta equals 0.2175. Therefore, the statistical power is 1 minus beta equals 0.7824. To end Chapter 8, pause the video and have a look at the left-tailed test, the right-tailed test, and finally, the two-tailed test. Observe the types 1 and 2 errors and the statistical power. What is the relationship between the type 1 and the type 2 error? The type 1 and type 2 errors are inversely related. As one increases, the other decreases, as depicted in the following figure. Usually, the type 1 error rate is set in advance by the researcher. It is also referred to as the significance level, alpha. The type 2 error rate for a given test is more difficult to know because it necessitates estimating the distribution of the alternative hypothesis, usually unknown. This is illustrated in Figure 8.7. Find more solved problems in our textbook. For more lessons on descriptive and inferential statistics, check out our textbook, Illustrated Statistics for College Students, available on Amazon. Thanks for watching.